Assalamu alaikum everyone. Today we are going to discuss the ARCH and GARCH modeling on our studio. And for that, first of all, we'll discuss the prerequisites of when we use this model. And then later on, I will make a flow chart of discussing how to process this model. So let's go towards this slide. So this ARCH-GARCH model, the full name is Autoregressive Conditional Heteroscedasticity, means ARCH, and Generalized Autoregressive Conditional Heteroscedasticity means GARCH models. And they are used when the series or the data have non-constant variance. What it meant to say that if you split the data into regions or into 2 or 3 time periods and you compare their variances, and you will find that their variances are not equal. So these data sets have a conditional heteroscedasticity, means their variances actually are function of some other things. So means their variances change in time. So this property is usually evident in the data sets which have high frequency, like daily data, weekly data, or a monthly data. So data sets like share prices, forex prices, exchange rate, oil prices, the data which is available in high frequency are used to usually have this property of non-constant variance. So unlike other models, it estimates 2 equations, one for the mean and other for the variance of the data. So it means in the first equation, the dependent variable is the actual variable. In the second equation, the dependent variable is the variance of the data. Okay, so this way there are 2 equations are estimated in this data set. Okay, now we will go towards the flow chart. Let's discuss the flow chart of this model. So first of all, when we are going to estimate this model, we need to make sure that data is normal. So we check for normality. So if the data is normal, then we can resume the process. So I will add yes or no. So I will add that child. So data is normal. Use as it is, and if it is not normal, then take a log. So what we do is that let's add is normal and is not normal. So normality test will give us 2 outcomes. Either the data will be normal or data is not normal. So let's move it here. Let's move it out. So yes, so if data is normal, we'll use it as it is. If it is not normal, then we'll take a log. So next, the process is I will move from the log side so that we can extend it. So if we take a log, then we need to check if the data has, we'll check for stationarity. So we'll check for stationarity. So this ARCH-GARCH model, since it is estimating the variance of the data, so it is assuming that mean should be constant. So what we'll do is, so we'll check for stationarity, and so if the data is stationary, then we use actual level data, and if data is non-stationary, we use the first difference of data. Okay, so unit 2 test will give us two outcomes. Either the data is stationary, which means its mean is constant in time, So we don't have to assume it's proved, so we'll use the actual data. But if the mean is non-stationary, means the mean is not a function of time, a mean is a function of time, so data is growing in time, so the mean equation should be made constant. So what we'll do is we will use the first difference data, and then another step is that we'll use a connector here, that when the data is normal, so we'll check the stationarity directly. So let's pick it up, and so rather than taking, we skip this step, and when the data is stationary, so we will move forward. So we have now this. So next step is we'll make it from the first difference side. So when we already made the data first difference, so means we have now confirmed that data is stationary. Then we need to confirm that data has non-constant variance. So we use the variance ratio test. So variance ratio test. So if you look at the data chart, you will know by looking at it the data is non-constant variance. We will show it in the R file, but sometimes it's not confirmable from the data visualization that the data has a constant variance or not. So we'll use the variance ratio test. So variance ratio test may say that variance is constant or variance is not constant. So let me write here, I write it wrong. So variance is constant, so let me highlight it to R. So if the variance is constant, we cannot use arch and GARCH model. We'll go back to use AR, ARMA, ARIMA models. Okay, go use ARMA models. So we'll discuss ARMA models in our file, and if the variance is not constant, we'll use ARIMA with arch / GARCH models. Okay, so let us label it. So variance is constant and variance is not constant. Okay, so we have this process. Now we'll select this one and then add it to our data and go with the variance ratio test. So this way, this steps. So ARIMA is standard. We will discuss it later on. And in both cases, when we use ARIMA model, what we'll do is we'll find lag order, the appropriate checking appropriate lag. Let me go here. Appropriate lag for AR and MA. So we'll check for appropriate lag orders. So that's same for here. So let's put it here. See. So we'll have appropriate. So F2 copy and we'll add a child here and paste. So both cases will check appropriate lag model. So it has a process. We'll discuss it. When we have an appropriate ARMA lag model, we'll estimate a ARIMA model and we'll check for its diagnostics. Okay. So after ARIMA model, we'll check for arch effect. So after estimating ARIMA model, if there is an arch effect, what we'll do is that, let me see. So if there is no arch effect, we will stay with ARIMA model, and if there is an arch effect, then we will go towards arch GARCH model. So let me move it here. So let's label it up. So if there is no arch effect, we use the ARIMA model, and if there is an arch effect, we use is yes arch effect will go towards arch and GARCH model. So this way we are selecting models. So we'll stay with the ARIMA model, mean we are here, so it's same thing. So appropriate lag order and then select it with this. So let me select it here and stay here. So this way we'll stop it here. But if we go with arch and GARCH model, then we'll check for arch and GARCH appropriate arch and GARCH effect. So how we can do it, that we'll just add on the so here what we'll do is we will add on arch and GARCH components until the diagnostics are clear. So let me check here. So we will carry on estimating arch. So this is the diagram of arch and GARCH model. So let me summarize it again, then we'll go towards RStudio. So first of all, we check for normality. If the data is not normal, we'll take a log or do the appropriate transformation. What we can do is we can normalize the data, okay, or use it as it is. If it is normal, then we'll check for stationarity. If it is stationary, we'll use the data in the level form, mean the actual data. And if it is non-stationary, we'll take first difference, and then we'll check for variance ratio test. If the data is stationary, we'll check from the level data. If it is non-stationary, we'll check for first difference data. And those data sets are already in the natural log or actual data form. And if there is variance is constant, and we'll use the ARIMA. And when it has not constant, we choose arch and GARCH, and then select appropriate lag order, then check for arch effect. If arch effect is not there, so we'll continue with the ARIMA model, and if arch effect is there, we'll go with arch and GARCH, and we add on lags till the diagnostics are clear. And what is the purpose of this model? So the purpose of this model is we'll use it to do forecasting. So the major purpose of arch and GARCH modeling is to make a model that helps us to do forecasting. The advantage of this model is you haven't seen any new independent variable. So we are actually extracting the data from the data itself. So this model is good for people use it for forecasting, because we don't need a new variable to forecast this variable, because if we take a new variable, we have to forecast that one too, so that we can forecast this variable. So we use it for forecasting if there is a GARCH. But if we are using a ARIMA model, it can be used for forecasting too. This way, let's put it here so that arrows are, yes. So it's visual. So this is the process of arch and GARCH model. So in this diagram, there is one more step missing. So I assume the data is maximum I1, but it can be more than I1. So what we can do is we can add here parent. Yes. So we can add here is check for stationarity again. Why we check for stationarity? Sometimes variable is I2. They are integrated of order 2. So we check for stationarity, and if let's add a child here. Okay, no, let's add a parent here, and we get if it is yes. So no need to add a parent. We add a child here. So it is we use the first difference data and add a parent here. We use the second difference data. So let's add it up. So this line should be removed, and this line will go to variance ratio directly, and this line is there, and this line should also go here. Okay, so let's move it out a little bit so that arrow is reviewable. So here it is non-stationary, and here it is stationary. Okay, so this way there is another step. So this way we can move out with the data. And there is another test that we can do is, so for that I will draw an example here, and then we can discuss on it. So let me check. Okay, so this diagram is complete. The another things left are minor details. We will go for it when it's needed in the R Studio. So this diagram gives us the process. So let's go towards R Studio and then build on it. Okay, in R Studio, what we do is that we will, let me zoom it up, the code, so that you can see it properly. Yes, these are the codes. So for Arch and GARCH model, there's a big set of libraries that are needed. So first of all, this is rmlist.ls. This command is used to remove all previous commands so that it clears up the screen, and then you can use other commands. Then there are libraries. Let me discuss them one by one. First is fin.ts. It's financial time series. It's for Arch tests. Then RU-GARCH. It is for GARCH models. In this tutorial, we will not go in this tutorial library because it is the complicated GARCH models. If the ARCH-GARCH model, simple ARCH-GARCH model are not able to estimate, not able to clear the issues, then we'll go towards RU-GARCH. Then there's T-series, time series library, which is for unit 2 test. Then DIVA NLM, which is used to add lags in the model. VARs is used to do the VAR, and sometimes it is required here. And vol test is used to check the variance, the significance of the variables if it is required. Then LM test is for the brush pattern test. Broom is used for table presentations. CAR is library used for robust standard errors if we need to estimate. Then there's a library command sandwich, knitter, forecast. ggplot is grammar of graphics plot. So it's used for graphing, it's used to make graphs. PDFetch is a library from which you can import financial data. So in this tutorial, I have imported one data. So I will show you. Then TS box is time series box. It is for time series tests. Stats is used for standard time series statistics operations. Then there is zoo for, similarly it's used for doing the diagnostic and statistical operations. Then VR test is variance ratio test. I will highlight them all and run. And for you may have to install it one by one, and because it's all installed in my computer, it is using all of them, so it's not giving error in any one of them. It's just saying let me show you the output so that you can understand what is the meaning of these outputs. So let's go. So it loaded the library. It says that it has clashed with zoo, so it is loading. It requires zoo, so it is loading zoo automatically. Then RU-GARCH said that it requires stats, so it is loading the stats too. T-series requires zoo, so it is loading zoo. And then there is the divine LM is clear. VARs required these libraries, so it is loading in the background. And then these are clear. LM test is clear. Broom is clear. CAR requires CAR data. It's already loaded now. So sandwich is already loaded here. Knitter is loaded clearly. Forecast is loaded. It says that forecast requires it requires FINTS, so it's loaded earlier. Then ggplot, then pdfetch, esbox, stats, so all are loaded. So if the library is not installed, it will say that library not found. Then you will go in tools and install packages so that you can install that library with that specific name. Let's move down. And now I will set theme black and white so that the graphs that it will make, it will be shown in black and white color, so that if you are printing it, it will be compatible with the black and white color combination. Okay, so its theme is set. So all the graphs that it may show will be converted into black and white when needed. So the library that I'm using is PDFetch, and I'm collecting data from. I'm not using this data. I'm using the data from PDFetch Yahoo Finance. So how to get the data? You go in help and write a PDFetch, and you will be able to see if you go in index, you will be able to see many types of. So it's BLS data, Bureau of Labor Statistics, and Bureau of Bank of England, Bank of Germany, European Central Bank, and then there are all others. So I use the Yahoo Finance because all of the data are annual. I don't know if any one of them have a quarterly or monthly data. So I use the Yahoo Finance to, and in Yahoo Finance I selected the data of this library. So it's shown here is GSPC. So I use the GSPC dataset. So I use this command pdfetch Yahoo. So df equal to pdfetch underscore Yahoo, and I'm using the close price of that company, of that share, and the index is GSPC. So when I load it, it will download the latest data from the website. So it means every day you open the data, you will have one new observation in it, and it means it's updated data. You can update your information every day. So when you open it, it will take time to load. So you will see it's the data starts from year 2007, first month and day 3, and you go down, it is up till year 2020, day 12, month 6. So it's yes, up till yesterday. So it's a latest data, and it has around 3,379 daily observations. So it's a good data. Now we have to tell that that it is a time series data. So how we do it? So DFTS means data file time series is time series setting. So select the data file, starting date. So my starting date was year 2007, month day 3. How I found day 3? It was January 3rd. So it is third day. Then end at year 2020, day 161. So how I found it? So I counted out that how many days has passed. So 6 months, 6 into 30 plus 12. So it is 161. So it means that this is the end data. And then frequency is 365, means annual. So when I run it, it will declare the data as time series. And when if I wanted to see the data, it is dataframe.ts, because the data is not openable now. But you don't need to see it because it is same as the DF. So it's just to show the command that how to see the data file. Now we'll make graphs to see if the data is suitable to do the arch and GARCH model. So for that, plot.ts, dfts. So because in data file there is only one variable, so I don't need to name the variable, it's only dfts. So if there are two variables, what I will do is I will add a opening square brackets, comma, and variable name. So variable name was GSPC. So this way I can call the variable if there are more than one variable, but in this data file there is only one, so no need to name it. So I will remove it and then run. So this is the data file. Now you can see the data if you zoom it up. Let me make it bigger so that you can see the data file. So note down that it has, if you add, let me annotate here. So if you draw a straight line here, this, so you can note that the variance is different. So at this point, this much was the variance. At this point, this much is the variance, and the variance is the little here, almost no variance here, high variance here, high variance here. So it has non-constant variance. It means if I split the data into years, so means from 2008 to 10, it has a different variance. From 10 to 12, it has a different variance. 12 to 14, it has a different variance. 14 to 16, different variance. So this data has different variance. So it is hinting us that it has it is a candidate for to be used as arch and GARCH model. So let's cancel it up. So if you want to add a title, then run this command title, and if you run it after the graph, it will add a title on it, so that when you download it, it will come as a title and the data file. Okay, then we can also make an histogram. So histogram at IST, data file, title name, frequency required false, color gray. So when I run it, it has a histogram. So you can note down here is that let me show frequency here true. What will happen? So it is showing frequency, and if I do it false, what is doing here? It is showing the density. So it is the density function, and if you do the on, it is frequency function. So you can note down that the peak is not in the middle, so it looks like data is not normal. So now, but we will confirm it later on. Next we go towards the first difference graph. So plot.ts, DIRF means first difference, and then by label and the title. So when I run both again, so you can note down. So it's the first difference data, and you can note here that variance is not constant here too. That's bigger. So it has different variance here, difference variance here, very high variance here, high variance here, and then so it's a noisy data. So when the data is a noise, then it is candidate for ARCH and GARCH modeling, because we propose that the changes in the variances are actually function of past variances or past of the variable. So rather than adding more variables, we use the history of the data to forecast the present of the data. So now we'll go towards normality test. So it's a Shapiro test is used for normality. When I run it, so it shows the Shapiro will test. So you can see here is the probability value is less than 0.05, and the null hypothesis here is, let me write it up. So null hypothesis is data is normal, but the variance p-value is significant, means data is not normal. So we'll move, we'll take the log. So the command used is df1 equal to log of df. So when I run it, it will make a new data file and it will be converted into log. So it is smaller. So note down here is that I have made a new data file. If you wanted to create a new variable within the same data file, the command is df select and df and pipe and then mutate and then give a variable name log series equal to log of GSPC. This way you can create a variable that will be added into the same data file, but we are not using it because when we do the process, then we have to declare the variable name and the command will become bigger. So that's why I made a new data file, so that I only have to tell this is a data file. I don't have to give the variable name because there's only one data in the data file. Now I will plot the data file which are in natural log. So when I plot it here, so you can see its variance is a little bit smaller. So it was a lot higher when we use the not log. So now second thing you can see is that you can go back and see the previous graph. So previous plot, previous plot, previous plot. So see here, there the variance is very high, and come back to the original plot, the variance is a little bit lower. So data is converted into normal data. Now we'll check for variance, if its variance is constant or not. So it's auto.vr. So it's a variance constancy test. So data file ARY, so data file to not found. So its spelling is actually df1. So back to the code. So when I run it, and it will take time, and so its statistic value is this, and it is very big. So it means it's significant, and means the data is not, the variance is not constant. So null hypothesis is the variance is constant. So now so it means we'll use the ARCH and GARCH modeling. Now we'll go for the normality test. So a unit 2 test, that is augmented Dickey Fuller test, data file 1, variable name, lag order 3. So you can change the lag order to any if you want, but it doesn't matter. All we need to see is if it is stationary or not. So here the test is there, so it is insignificant. Okay, so insignificant means that the null is accepted, and null hypothesis is that variable data is not stationary, and alternative is stationary. So data is not stationary. What we'll do is we'll take the first difference. So data file 2 is diff of data file 1. When I run it, it will make a new data file, which is first difference of data file 1. It has one NA, we have to remove it. So df2 is na.remove df2, so it will overwrite and remove one observation from the start. Okay, then we'll do the unit 2 test again on this first difference data, and you can note here is that it is significant now, and it means it is selecting alternative hypothesis. So data is stationary, so it means we will use the first difference data. Okay, so we can also check we don't need to check the variance ratio, but we can check it for first difference too. Now, first of all, we need to estimate how many lags of AR or MA are needed. So for AR model, to see MA components, so let me write it here. So what are the MA components? So MA component is known as moving average component. It checks how past random shocks affect the present value of data. So how we add it? We just add the past error term if we need MA1. If we need MA2, we take the second past 2 time period previous error term. So we know that present error term is unknown, but the past error term is known for us in the regression, so we can compare it. And second is the AR component. AR component is known as Autoregressive component. It checks how much inertia is there in the data, means how difficult the new value is, how difficult is the new value to change with respect to the past value. So if we need to add AR1 is incorporated using first lag of dependent variable. This way we add these two components. So these are two types of information that is available in the past. Okay, so AR and MA. Okay, so let's move forward. Let's clear the screen. So how to check how many AR or MA needed? So to check for MA component, we make ACF plot. It is auto correlation function plot. When I make it, so you can see the first 2 lags are outside the blue line. So it means 2 lags of MA is required, MA1 and MA2. All others are inside. There are few outside later on, but we check for consecutive outside ones. So first 2 are consecutive outside. Okay, so and then we check for PACF, which is for AR component. And when we look at it here, so first one is outside only, consecutive first. So we need AR1. So it means technically we need ARI. What is the specification of ARIMA is P and I and Q. So P is the order of AR, I is the order of integration, and Q is order of MA. So here what we are hoping for, that is 1 AR, 1 integration, because we are taking first difference only, not the second difference. Then Q is 2. So ideally this model should be estimated. But since our data is too long, it has 3000 plus observations, so we can have a bigger lag order. So what we can do is that we will use the auto.arima function. It will find us the lag order automatically. So that when we do it, so it is giving us 001. So it is just saying that we should keep 1 MA. But since we are already giving it first difference data, so it is proposing us ARIMA equal to 0, 1, 1, because I have given it a first difference data, not the actual data. So but if I give actual data, it will give me 0, 1, 1. Okay, but you can check it out yourself. So this way you can confirm the. So we will estimate the same model. So we'll pick the data file 1 and tell us to estimate 0, 1, 1, and when I run it, it will give me the same answer that was shown here. But when I say it to give me summary, so MA1 is there. So its interpretation is that if there is a random shock in the previous time period, the present value of the GSPC share price change will decrease by this much. So now present value is also in first difference. So and it's in natural log. So the dependent variable is actually GSPC growth rate. So if there is a 1% random shock in the previous time period, the present GSPC growth rate will slow down by 0.14%. So this was the interpretation of MA model. Now we can look for its diagnostics. When I do it, you can see it here. It will give me a diagnostic chart. You have to make it bigger so you can see if it is readable or not. So you can note it down here that there is only one component significant here in ACF, and that is because we have added 1, and all others are insignificant, means this lag order is fine. Then we can check for residuals. So when we plot it, so this is the residual chart. So first few are not outside and the data looks normal because it's in the middle, and this is the residual chart. There is no pattern in it, so there is still some volatility that ARIMA model cannot cover it up. So we have to go towards advanced model. So we can also check for stability. So since there is only 1 MA, so there is only one root. This dot should be within this circle so that the model is stable. So if I make MA2, it will show me 2 dots. If I make MA3, it will make me 3 dots. So this way, the stability is tested. So if I make AR1, so let's estimate another model here quickly and then see the auto plot. So let's estimate AR212. So what will happen? I will say 2 and 2 here, and then estimate, and then auto plot ARIMA 212. So what will happen? It will show me 2 dots for AR, 2 dots for MA. So all are inside. So it's saying model is stable. This way. Now the problem with RStudio is it cannot estimate both GARCH model and ARIMA models together. So what we will do is we will estimate the residuals of this ARIMA model using this command. Okay, and we can also see the plot of these residuals. We have already seen it. So this plot is showing us same thing that was shown earlier. So it does not have any AR or MA effect remaining. So it means ARIMA model is clear. We don't have to add more lags, but there is still some volatility. So we'll use these residuals in the ARCH and GARCH models. So since we have the residual generated, now what we'll do is we will estimate the mean equation. So ideally, when in other softwares you can estimate ARCH and GARCH model and ARIMA models together. So what you can do in that model is you can estimate the mean equation and add AR and MA components in this equation. Since we cannot integrate both models together, so we have estimated the ARIMA model and calculated the residuals mean, what is left behind, and then we'll use that data in ARIMA modeling. So GSP mean value, the mean equation is dynamic linear model and it's only constant equation. So there is no independent variable in this equation. So when I do summarize, it will give me the mean value. So if you have a good ARIMA model, then ideally the mean value should be insignificant. It is insignificant here. So it means that you are able to capture any mean effect in the data by using an appropriate ARIMA model. So everything that is left behind is the volatility in the variance, but no changes in the mean value. So it means you will focus on how to make a model on volatility. So now we'll go for to check the arch effect. So for arch effect, we estimate the residuals and square it up, and then create its regression of residual square with the lag of residual squares. Okay, and then show its regression results. If it is significant, there is an arch effect. It means the square of residuals, past square of residuals are explaining present square of residuals. Means residuals are function of their past. And since it is a square of residual, we call it volatility. So square of residuals are volatility. So the volatility is a function of past. So it means it is conditional volatility. So that's why we go for arch model. Okay, so we can check for the effect using this command. This is the chi-square test. So the result that is shown here is the chi test is not working. So because what is happening? Let me see which command is not working. Let me see. So it says that the GSP arch. So it is arch effect, arch EF. Spelling was wrong. So that's why it is giving us wrong error. It's giving us an error. So when I run it, so it is giving a chi-square test value. It is big. So it is showing us that there is an arch effect. But we can confirm it using this command, this arch test command. And when I run it, so it is significant, means there is arch effect, because the null hypothesis is no arch effect. So it's confirmed that there is conditional volatility in it. And since the volatility is function of past, so it's autoregressive conditional heteroscedastic volatility. And if you cannot control the volatility, it becomes heteroscedasticity. That's why the name arch has been used. So if you ignore the volatility and run the model, and the volatility will become heteroscedasticity. Now we'll go towards the estimating the arch and GARCH equation. So GSP arch is GARCH model, and we'll start with 3 arch effect, and GARCH is 0. So now first of all we'll discuss what is arch and GARCH. So let me write it here. So arch is, we already studied autoregressive conditional heteroscedasticity is same as AR component, but except the we use lag of variance rather than lag of dependent variable, and it also checks the difficulty in which data is changing in time. So same as AR effect. And the GARCH is same as MA model, MA component, except we use error. We use past error of variance equation rather than past error of mean equation, or the ARM actual equation. So this is arch and GARCH effect. So when you are difficult to understand, just assume that arch and GARCH are same as AR and MA, but they are for the variance equation. Let's clear it up and let's go with the equation. So I will start with some reference value. I'll say that I will start with arch 3 and GARCH 0, and I will use the iteration 500. So I will estimate 500 times until the model is optimized. but if it is optimized before 500, it will give us a result. Otherwise, it will give us an error. So the first item in the C brackets is the GARCH effect, and the second is ARCH. So let's estimate it. So it has done its background calculation, and then when I say show me the results, so so it will give me the 3 arch component. All of them are significant. Okay. So and you will stop the point where you will see the box lesion test is insignificant. Okay. So we note down here that the residuals are almost insignificant. It's 0.9. So what we can do here is add one GARCH, confirm if it is improving. So yes, if I add one GARCH, so 3 arch and 1 GARCH, and you can say that the second arch is insignificant, and so the test is clear. So it means this is an appropriate model. Okay. Then what we can do is we can estimate what you need to do is you need to estimate the volatility. So the volatility chart we need, how we estimate. So in some research, people estimate the unstable portion of a data. So if your data have high frequency, you can use ARCH and GARCH model to calculate the volatility. That volatility is the unstable portion of a data. So we call it unstability. Suppose you are estimating the unstability of GDP. So if you have a GDP data with high frequency, you can use this approach. But if you have a data with low frequency, you can take the residuals that we generated in the ARIMA model. That was this residuals, ARIMA R. This is the unstability for the data set which have small frequency, and these residuals are the instability for data sets which have high frequency. So when I run this and then plot it, so it will show me the volatility of the change in GSP, because we have used the GSP change data. So you can see their volatility. So this portion is unpredictable. This portion. So all bars which are high are actually the unpredictable portion, or the portion where there was some unknown change or unexpected change occurred. So what we can do here is we can study this time period, what happened here, what happened here, and what happened here. This is the coronavirus case because this data is up till this month. So this is the case of coronavirus, and other shocks are here. So this way you can study what went wrong or what went right. Then you can store this data file, the data variable in the data file using this command GSP arch $fitted values. And if you want to store it, so you can write it out that volatility is equal to GSP arch. When you run it, so it will give you a new variable, and you can see it here, vol. It will be shown here somewhere. Yes, so it's a time series data. So this way you can store the data file, and you can look it up by writing only name or only vol. So when I run it, you can see the data. So here the volatility is here. So the first column is the volatility of the data. Okay. Now since you have used 3 AR, so first 3 values are wasted. So every time you add a AR, first value is removed, AR2, first 2 value will be removed. So this way you estimate ARCH and GARCH model. Hopefully you understood the mechanism. The code file will be available. So you can redo it, but since I was discussing it one by one, you can copy the codes, write down and your RStudio so that you can estimate it. Thank you very much.